Research on RFI anti-interference filters in measurements of conducted disturbances for an induction heater. The plan of presentation. Introduction, EMC tests, experimental setup, simulations, preliminary tests, results, conclusions. Electromagnetic compatibility is a critical aspect of modern electrical and electronic device design. It ensures that devices operate correctly in their electromagnetic environment without causing or suffering unacceptable interference. The concept encompasses both emission control, preventing devices from emitting unwanted electromagnetic energy, and immunity requirements, ensuring devices are resistant to electromagnetic disturbances. Electromagnetic compatibility is the ability of electrical or electronic devices to operate satisfactorily in a specific electromagnetic environment without causing excessive electromagnetic disturbances in relation to other devices operating in the same environment. The modern world depends on many electrical devices and systems, which makes EMC very important because the devices are part of larger systems responsible for the correct operation and development of an industry or economy that requires high efficiency, including immunity to electromagnetic interference or generally interference signals. This study introduces an innovative approach to the design of anti-interference filters for an induction heater, focusing on the effectiveness of suppressing conducted disturbances. The novelty of the research lies in the application of a combination of low-pass filters and common-mode chokes with varying parameters, which allowed for compliance with stringent EMC standards. Each device manufactured in the European Union must be marked with the CE mark, which means that it meets all EU directives. Directive 2014/30/EU of the European Parliament and of the Council of 26 February 2014 on the harmonization of the laws of the Member States relating to electromagnetic compatibility is the overarching directive to which the Polish Act of 13 April 2007 on electromagnetic compatibility is also subject. The subject of the research is an induction heater that was installed in an electric boiler for heating water. Water heating is achieved by two windings in the form of induction coils that transfer energy to the internal walls of the boiler made of ferromagnetic material. The basic parameters of the tested induction heater are presented on the slide. In accordance with the PNN 55022 standard, the conducted disturbance testing station is subject to strict regulations. The block diagram of the laboratory station, consisting of a measurement system and an induction heater. The line impedance stabilization network is a device used for EMC testing. The listen system consists of sets of separation filters designed to filter out interference coming from the power supply network, redirecting interference generated by the tested object to the output intended for the EMC receiver or analyzer. Moreover, the network simulator prevents interference emitted by the tested objects from entering the public power supply network. The artificial network from Hameg was used to set up the EMC test station. The spectrum analyzer is designed to present current signal waveforms in the frequency domain. The spectral decomposition is made possible by using the fast Fourier transform FFT operation. Its use allows you to obtain information about the number, frequency and amplitude of the signals that make up the tested input signal. At the initial stage of designing and building the filters, computer models of the filters were developed, and then simulations were carried out to select the filter with the best filtering characteristics. The transfer function graphs clearly showed that regardless of the inductance of the common mode choke, the filter with the largest capacitor had the lowest cutoff frequency, which means that the filter began to attenuate the signals, reaching it more quickly. In addition, a higher value of the common mode choke inductance causes a steeper characteristic, which is also associated with a lower cutoff frequency. The test results are presented in Figure 5a, which shows that devices operating near the induction heater did not cause excessive interference. Limits were not exceeded and no disturbing peaks or anomalies occurred. From a frequency of approximately 2 MHz, the disturbances maintained a constant value of approximately 24 decibels microvolts. Then, an electromagnetic compatibility test was carried out on the induction heater itself, without the use of any filter. The device was connected to the input of the artificial network and measurements began. The results of the experiment are shown in Figure 5b. As can be seen, the induction heater did not meet applicable standards. In the range from 150 kHz to 8 MHz, disturbances significantly exceeded the average and quasi-peak limits and reached levels of up to 90 decibels microvolts. Only at a frequency of 18 MHz did the disturbance level drop below the average limit. Such a device would not receive a positive opinion from the entity conducting the tests, which would result in the lack of CE certificate and sales approval. For the purpose of testing the electromagnetic compatibility of the induction heater, 10 filters were built, including 6 first-order filters, consisting of passive elements with different parameters and in different configurations. The elements necessary to build the filters were mounted on printed circuit boards. All filters were enclosed in metal housings, and during the tests they were connected with a protective conductor to the tank housing to equalize the potential. The lack of a capacitor in filter number 1 caused differential disturbances in the induction heater system. The disturbances significantly exceeded the level of 80 decibels microvolts, and the test graph of the induction heater with filter number 1 was slightly different from the graph of the induction heater without a filter, which meant that the filter did not have any filtering features. Filters number 2 and number 3 equipped with capacitors attenuated the signals, especially in the initial frequency range. The disturbance level dropped from 90 decibels microvolts to approximately 55 decibels microvolts, but this was insufficient to meet compatibility standards because the disturbance generated too many peaks above the average disturbance level. An increase in attenuation as the capacitor capacity increases is visible. The use of a common mode choke with a low inductance value 1.82 microhenries in filters number 4 and 5 resulted in a reduction in the disturbance level by approximately 20 decibels microvolts, which also in this case prevented the heater from passing EMC tests. The filter with the larger capacitance attenuated the signal to the expected value at a lower frequency than the other, but then suddenly amplified the signal beyond the average limit. In addition to the classic filters with common mode chokes, filter number 6 was built, consisting of 2 coils with a wire cross-section of 2 mm and inductances of 31.9 microhenries and 34.4 microhenries. Filter number 6 is also equipped with a capacitor with a capacity of 4.7 microfarads and a 1 megaohm resistor. The use of coils without a core, despite the use of a capacitor with a capacity of 4.7 microfarads, did not bring the desired effect, i.e. the induction heater with filter number 6 generated disturbances at a similar level as the heater itself without a filter. After reaching the frequency of 2 MHz, the signal was amplified and exceeded the level of 90 decibels microvolts. Filter number 7 is composed of 3 simple filters, so it is a third-order filter. It had a common mode choke with an inductance of 6.6 microhenries and 4 coils with values of 6.04 microhenries, 6.06 microhenries, 6.4 microhenries and 6.01 microhenries. The use of a common mode choke and 4 similar coils reduced the noise level by 25 to 30 decibels microvolts. There were peaks exceeding the quasi-peak limit, which is not permitted by the current standard. The device using this filter did not meet applicable standards. Filters 8 and 9 are created by combining filters 4 and 7. In the 8th filter, The output of the fourth filter is also the input of the seventh filter. The ninth filter is the inversion of the eighth filter, so the output of the seventh filter is also the input of the fourth filter. The responses of filters 8 and 9 to the input signal were very similar to each other. Both responses did not exceed the quasi-peak elimination limit. 2 and 1 peaks exceeded the average limit, respectively. In the ninth filter, smaller ripples could be seen in the range from 0.5 MHz to 2 MHz compared to the eighth filter. The induction heater with filters 8 and 9 met stringent EMC test conditions, which would enable its legal use. The filter number 10 was created by combining two low-pass filters with the same common mode choke, inductance 12.9 microhenries, and 1.5 microfarads and 2.2 microfarads capacitors. The study showed that the filter number 10 had the best filtering features. Throughout the entire frequency range, there was not a single exceedance of even the average limit. The highest level of disturbance reached 48 decibels microvolts in the initial frequency range. Moreover, from the Bode plot it could be concluded that the frequency at which the attenuation was 3 decibels was 20.8 kHz. This means that the filter attenuated at frequencies that had not yet been taken into account during the test, because the test range was between 150 kHz and 30 MHz. Moreover, the graph below shows a slope of 20 decibels per decade, which means that for every 10-fold increase in pulsation gain drops by 20 decibels. Simulations allowed for the preliminary selection of potential solutions, which were then verified through empirical tests. These results confirm that properly designed filters can effectively suppress conducted disturbances, which is necessary to meet EMC standards and allows for the legal use of electrical devices on the European market. Conducted disturbances, i.e. disturbances traveling along power cables, cannot be avoided, so it is always necessary to include a noise filter when designing any new electrical device. Designing systems with inductive elements based on simulations is difficult due to many nonlinear phenomena and does not reflect the behavior of the filter in reality. 10 anti-interference filters were built, 3 of which had satisfactory filtering features that made the induction heater meet electromagnetic compatibility standards. Even though the first-order filters do not meet the standards, according to the simulations and EMC tests, it was found that as the inductance of the common mode choke of the filter increases, its falling edge becomes steeper. Significantly better results were achieved by 2- and 3-stage filters, in which series connection of simple filters resulted in significant reductions in disturbances conducted and, consequently, compliance with stringent standards. References. Thank you for your attention.